In this video we're going to be looking at scatter graphs, and we're going to go from grade 4 right upwards. So starting off is the kind of classic scatter graph question you might see and you're more familiar with. So you've got the value of cars and a used car garage are recorded below, and the scatter graph shows this information. So the value is on the y-axis and the age in years is on the x-axis. And the first thing is you're told that another car arrives at the garage. It is 4 years old and worth £5,000. For 1 mark, show this information on the scatter graph. So this is very simple. It's 4 years old, so I go to 4 years and it's worth £5,000. So from 4 years, I then go up into £5,000, which should be there, and I just put a little point on there. Okay, so we've now done this. Now the next thing I'm asked to do is describe the correlation. Now there's sometimes a bit of confusion here about state and describe. If you're not sure, I recommend doing both. Now the type of correlation this is, it goes downwards, so just like with gradient, this is negative, it's going downwards. So if it just said state the correlation, I would just write negative correlation. Okay, negative correlation. However, it says describe, so I need to kind of say, what does that mean? What it wants me to say is, as I go along here, as the age gets older, what happens to the value of the car? As the age increases, the value here is going down, the value of the car decreases. And that's what I would write. As the age increases, the value of the car decreases. And I've written it underneath so you can actually read it. So that is part B. As the age increases, the value of the car decreases. Okay, let's look at part C. The next car that arrives is 6 years old. Estimate the value of the car. Now note, this is worth 2 marks, and this is why. They don't tell you, but they're expecting you to draw a line of best fit, and this is why. If I went to 6 years and went up, would I stop there? Would I stop there? Would I stop there? When would I stop? I don't know how to stop. So what I need to do is I need to draw a line of best fit. Now a line of best fit needs to go through the data, needs to go through most of the data, and you want it basically that the distance from a data point to the line is the minimum possible. Imagine it's a road and you want everyone to live, if everyone lives at a data point, you want these people to live as close as possible to the road. Now obviously you're going to use a ruler and it could look something like this. Okay, so there's my line of best fit. And it's around the middle of the data. Okay, now you notice hopefully that I've extended it all the way and it's going to go through here, and you'll see why that is in a minute, but for now it's generally useful just to put it through the graph as much as you can. Okay, so we're now doing the next car that arrives is 6 years old. Use it to estimate. One of your marks is usually for drawing a good line of best fit and then being seen to use it. So that's what I'm going to do. I'm going to go from 6 and I'm going to go up until I hit my line, and then I will go across from my line. Okay, and if I look at my cost now over here, it is 1 blob above 4,000. Well, there's 2 blobs between 4,000 and 5,000. So each one must be worth 200, which means this is worth £4,200. Now everyone will have a slightly different answer because you will have a slightly different line of best fit, but they allow a degree of accuracy, so that's fine. Okay, I'm now going to add another part of the question, and this is sort of taking it to the next level. Okay, so we're now looking, what we've looked at up to here, is sort of grade 4 stuff. We're now looking at grade 5. Find the equation of your line of best fit. So we're finding the equation of a line here. Now it's linear, it's a straight line, so it's going to look y equals mx plus c. Remember that m is the gradient and c is the y-intercept. Well, in this case, the y-intercept is when x is 0, so that's here. So here, where does my line of best fit go through here? Well, I've not extended it quite long enough, but it goes through there, which is 2 blobs above 9,000, so that's 9,400. So my y-intercept is 9,400, and that's my value of c. Okay, so now I just need to find the gradient. Now remember, gradient is the change in y divided by the change in x. In other words, what it means is every time I go across 1, how many do I go up? So if I want, I could go across one and see how many I go up, or I could use any 2 points on my line, recommending you use ones that go exactly through the corner, or I could use one that I've already used. So I actually already have 2 points. I've got this point, which was there, and I've got this point here. But as I said, you should be able to use any 2 points you want on the graph. If you want, you could literally just go across one and see how many do you go up if you go across one. Sometimes it's a little bit harder to see than it is on this graph, so I'm going to do the equation here. But if you want to just go across one, and from here to here, how many have I gone up? Well, I've obviously gone down, so it'll be a negative gradient. But let's have a look. So if I look between this point here and this point here, my change in y has gone from 9,400 to 4,200. So to get from that 9,400 to 4,200, I take away 5,200, and that's taken me 6 years. And I could use a calculator for this, or just simplify it and see what the answer is going to be. And that will give me negative 866.6 recurring, so 6, 7. Now a couple of things to note there. First of all, that's slightly different from what you get if you just looked along one and how many up or down you go. That's because it's more accurate the further apart your points are, because at this close it's hard to see exactly where is this line of best fit and how many points up or down is it going. Second of all, you notice this isn't a nice number. Often when you do equation of a line you get 5 or -1 or a half. The reason it's not a nice number is because this is real life maths, and in real life the numbers often don't end up being easy numbers, but in real life you're allowed to use a calculator, so it's not too much of a problem, but it might look a little bit disconcerting. Okay, well that's the value of my gradient, so I'm going to put y equals negative 866.67 x plus 9,400. What does that mean? That means every time I go across 1 year, my car loses £866 of value, which isn't great. So every year it's going down, depreciating by that much money. Okay, the last thing I'm having a look at how to do is using my equation to estimate the cost of a car which is 10 years old. I apologise for the apostrophe, I've got no idea how it's got in there. I think it's autocorrected to that. Okay, and how reliable is your answer? So if I'm estimating it at 10 years old, obviously 10 years is beyond my graph, it would be there, so I could extend my line. Or what I'm going to do is use my equation. So I have 10 is the value of x, so I'm going to replace in my equation here x with the number 10. So I'd have y equals negative 866.67 times 10 plus 9,400, and that would give me £733.33, which is pretty similar to what we get if we extended the line, and not a great value for a car to be sold for after 10 years. How reliable is my answer? Well, it's outside any data I have. I don't have any information for 10 years. I don't know whether after 9 years it suddenly drops off or whether it stays the same. I've got no information, so it's outside my interval, so it's not super reliable, but it's pretty close to my interval, so it's quite reliable. Okay, I'm going to do another example, but this time we're just going to find the equation of the line of best fit. That's all we're going to do. We're going to look at these two graphs. We're only going to find the equation of the line of best fit of one of them. I just want to bring something to your attention. So they both have the equation, they both have the line on them already, but one of them is different from the other, and that's because this has this funny little zigzag. What that means is, even if I extended this here to this line, this isn't actually 0 for x, because x here, at that point, well, that's 102, that's 100, that would be 98. That's not the y-axis. They've just shifted the whole y-axis near to us, so it's useful. So if you did want to find the equation of a line like that, where it doesn't have the intercept we can see, you'd have to find any 2 points on the graph and do the method you do between 2 points. Okay, but we're not looking at that at the moment. Let's just be aware it's different. So let's get rid of that one for now. And let's just look at this one. So it is a straight line. Let's find the equation of the line. Y equals mx plus c. I need the gradient and the intercept. Now this x here does go to 0, so I can just read it off. The intercept is there. That's 1.5 blobs up. Well, each blob is worth 2, so that's going to be 23. So my intercept is going to be plus 23. Right, now let's notice about this. This is positive correlation. It would have a positive gradient. And what this is saying is, as I do better on test 1, I do better on test 2 as well. Let's find the gradient. So remember, the gradient is every time I go across 1, how many do I go up? Also known as the change in y per change in x, or divided by change in x. I recommend using the point of the intercept as 1 point, and let's use another point which goes exactly through a corner. So I suggest, well, I'm not quite sure what I suggest, but if we zoom in a bit here, if we look here, that one is the same in the sense that it is 33 and that one was 23. So let's use that. Doesn't really matter which point you choose. So my change in y from 23 to 33, I've gone up 10. And how many have I gone across? Oh, well, I've actually gone across 10 as well. And 10 divided by 10 is 1. So my gradient is 1. So that means I could write y equals 1x plus 23, which we normally just write as x plus 23, but you could write it as 1x plus 23 if you wanted. And there we are, that's the equation of that line.